We will proceed with our scheduled workshop on reducing high dispersion spectroscopic data from planetary nebulae as planned. Well, let's start with this about planetary nebulae. In our case, we are going to apply spectroscopy to gaseous nebulae, in the particular case, planetary nebulae. We have here two examples. Of this type of images, one is IC418 and the other is M57. These images were captured using the Hubble Space Telescope, and they provide us with a glimpse of the characteristics of these objects, including their central star and the surrounding shell in the star's environment. Further explanation will be provided later. What is the importance of exoplanetary nodules in scientific research? As you can see, that thing about the star in the middle, planetary nebulae are a crucial part in the evolution of solar-type stars. As part of stellar evolution, stars like the Sun, for example, are converting hydrogen into helium. Subsequently, helium will undergo conversion into carbon, leading to the evolution of the star. Consequently, the stage of planetary nebula occurs when the star, having previously expanded its outer layers, proceeds to shed these outer layers. So, that is very important, not only because it is part of the star's evolution, but also because it is the way to chemically enrich the interstellar medium. Let's keep in mind that, for instance, we, as living organisms, possess carbon atoms, oxygen atoms, nitrogen atoms in our body, which were not formed by the Sun, but had already been formed by other stars in earlier phases, let's say, and were reused when the Sun and its planetary system came into existence. So planetary nebulae are without a doubt significant as a component of this slightly more comprehensive process in the grand scheme of things. Well, let's see. Here we have other examples of planetary nebulae in particular. Cases whose geometry, it is quite different from the one we just witnessed a short while ago. Here we have bipolar nebulae, quadrupolar nebulae, and what is referred to as point symmetry nebulae, which are those that have gas condensation symmetrically placed with respect to the central star. We cannot talk about an axis of symmetry, as in the case of a bipolar or elliptical, but rather the symmetry is point by point, okay? I mean, these represent diverse morphological forms and structures. Why does the gas in planetary nebulae shine? Let's talk about a process that is happening in planetary nebulae. The stars that are situated in the center of planetary nebulae are incredibly hot, and they are already in motion, displaying their dynamic nature. If they are not, they are already nearing the white dwarf stage. Therefore, what occurs is that the ultraviolet photons, which have very high energy, are able to photoionize the atoms in the surrounding gas, resulting in the ionization of the gas atoms by the high-energy ultraviolet photons. So here we are going to observe a brief animation depicting the process of photoionization. Witness the interaction of an ultraviolet photon with a hydrogen atom and its subsequent impact. And take a look at what is about to happen. Please come and release the electron from its current state. This phenomenon is known as photoionization, which refers to the ionization produced by an ultraviolet photon. The result of this process will be the generation of positively charged nuclei in our gas, leading to the sudden presence of loose negative electrons in the surroundings. So imagine how to have a gas, a fluid, but also not only responds to fluid equations, but also responds to electromagnetic interaction. That is, it is not only hydrodynamics that will explain these gases, but magnetohydrodynamics when it comes to ionized gases. Let us observe another phenomenon that also takes place in these gases and deserves our attention and scrutiny. Here what we are going to have is that one of these electrons, which are free, interacts with an atom that is neutral. And what it is going to cause will not be enough to free the electron, But later it will be enough to excite the electron that is there by giving it part of its kinetic energy. If the kinetic energy transmitted to the electron in the atom is greater than or equal to the energy required for the electron to move up a level, then the electron will undergo an upward transition. In this scenario, the electron gains enough energy to transition to a higher energy level within the atom structure. And that's what we call coalition excitement. So, let's see here. The process comes in the electron, and the electron comes out, deflected with a different kinetic energy than it entered. And if the disparity in kinetic energies, denoted by the equation we have up there, is at minimum equivalent to the disparity in two energy levels, then that electron will be stimulated to another level. This is a positive outcome. Good to know. So now we'll see recombination process. Let's think about the two cases we had. First, we had the case of plasma, that is the free electron and the nucleus around. So, there will be a recombination process when that electron is trapped again, and the energy it had in freedom will be released, the energy it had as a free electron, right? That is to say, this energy is going to dissipate as part of the continuum of ongoing events of the electromagnetic spectrum. However, it is highly probable that this trapping takes place at a higher energy level, in such a manner that spontaneously, because we are aware that physical systems tend towards states of minimum energy, spontaneously, that electron will decrease its level. And when it goes down a level, the energy it will emit will be exactly equal to the difference in energies between those two levels, and that will give us a particular photon. And what that will produce for me then is a spectral line. Let's observe the animation. In this observation, we can see the electron being captured by the atom and subsequently spontaneously descending to a lower energy level. This descent leads to the emission of a photon with a very particular energy. Energy is the difference in energies between those two levels. That is the energy of the photon. And that is very interesting because what it will produce for us is the photon of the same energy. That is, we will be accumulating that energy, and that is what will form the spectral lines in a spectrum. What do I mean by spectral lines? When we possess a hot gas and observe it through our spectroscope instrument. Here we position it as a network that travels wherever the light travels and subsequently interacts with the prism, which in turn displays the spectrum to us. Well, because there are only particular transitions happening at the moment, it is worth noting this limitation in the current situation. No transitions at all wavelengths or energies, but only at some in particular. So what we are going to have is that the light produced by that gas, because of the recombination effect, is going to be in certain spectral lines. So, that is why we have lines back there. We already know that we can see a white light bulb or white light, and it turns out that it is the combination of several colors. This is occurring in planetary nebulae. What is our objective in observing with a long slit? In the case of extended objects, and planetary nebulae are, we have a great deal of interest in obtaining information about specific locations within the nebula. We are unable to fit the entire nebula into our spectroscope, because in doing so, we could potentially confuse parameters that specifically pertain to certain locations. The function of the long slit is to obstruct light from entering the nebula except for a specific area, thereby preventing light from any other areas. Every single dot would represent a distinct slit, with the slits being exclusively painted yellow on their left side. Each of those dots is going to turn into a spectrum. In fact, it can be seen that when passing through the star, which is the brightest point above in the slit, when passing through the star, what is generated in the spectrum is the whole rainbow, as from the star. However, at the bottom, when passing through the nebula, only certain spectral lines are generated. Hence, in this manner, we can visually perceive in our detector the unique spectrum of each dot through which the slit has passed, offering valuable insights into the composition and characteristics of the objects under observation. And that will enable us to understand the physical characteristics of each of those small dots. Thus, when we encounter points of interest, we can compare them with points that are more typical or distinct. So in the case of Mezcal, what we have is that out of the entire visible spectrum, we focus on the spectral lines. To clarify, our spectral range, which normally spans from 3000 to 7000 angstroms, representing the entire optical range, is narrowed down to a few angstroms. This is done in order to observe how the line is deformed by the Doppler effect along the line. What is the Doppler effect? Maybe all of you can remember this sound that is possibly familiar to everyone. Equations for frequency change of a wave when propagated by a moving source. They describe relationship between wave frequency and source velocity, considering Doppler effect. Provide mathematical understanding of how wave frequency is affected by source motion. Thus, as evident from the equations are arranged in two columns. Positioned at the top of the left column is the relationship where the frequency equals the zero frequency, indicating the original frequency multiplied by a factor that pertains to the speeds. Up would be the velocity of the wave divided by the sum or difference, because it can be positive or negative, of the velocity of the wave plus the velocity of the source. The speed of the source is v with s. Well, since we are talking about electromagnetic waves, we change the speed of the wave in the following region to a c, which is the speed of light. The speed of light is 299,792,458 kilometers per second. In that way, the frequency deforms. It is multiplied by the quotient of the speed of light divided by the speed of light, plus or minus the speed of the source. This results in the original frequency being modified based on the relative speeds involved. Now we make another change, and that is that the frequency in the electromagnetic relationship can be written as the speed of light, c, divided by the wavelength, ll. Then we substitute the frequency in the third range for c between lambda, the observed one, and for c between lambda sub 0, the one that was originally produced. Afterwards we proceed to do we reverse the equation. That is, it's as if we obtain the reciprocal of both sides of the equation, which are fractions, and then we can eliminate the speed of light, or at least one speed of light that appears in both equations, by inverting the equation. That then leads us to the second column, where we have the wavelength equal to the original wavelength multiplied by the factor c plus or minus the velocity of the source divided by c. If we subtract the original velocity, that is, lambda 0, on both sides, then we can perform a trick on the right side and make the speed of light disappear completely, resulting in its absence from the equation. So, this difference between the original lambda minus lambda 0 would be something like how much does the wavelength increase or decrease in relation to the value it should have had in the first place. In our situation, we utilize the laboratory value. Therefore, the ultimate equation is delta lambda over lambda 0 equals source velocity over c. This is of utmost importance because it is crucial to notice how that straightforward formula clearly indicates to us that if we are able to perceive a difference in the spectrum in relation to a stationary source, such as a lamp on the ground, then that separation of the observed wavelength in relation to the original one is directly and unequivocally connected to the velocity of the source, to how the object moves through space and the speed at which it is traveling. So, that's why it is extremely important for us in terms of when we want to understand the morphokinematic structure of a planetary nebula. This principle, known as the Doppler effect, is utilized in conjunction with high dispersion spectroscopy to accurately determine the nature of this movement and its characteristics. The graph of the equations we are going to see are these. On the left side we have a stationary source, and therefore the radial waves are the same. And in the other point we have a moving source that, as it moves in the direction in which the frequency moves, increases in an apparent manner. At the back the frequency decreases and the wavelength increases, leading to an inverse correlation between the two. The audio example is well known to us because it is a type of wave that we are familiar with, specifically a wave of sound. Sound is a mechanical wave. It is not the same as light, which is an electromagnetic wave. However, this Doppler effect takes place in both sound waves and light waves, which are types of electromagnetic waves. The distinction lies in the fact that the wavelengths that our ear perceives as sound and those that we perceive as light differ significantly. This is primarily applicable to the situations we are currently discussing. Small those changes that only with our instruments we can see. I see a nebula, and with my eyes I couldn't know if it's coming or going, if it's moving away or approaching us. However, with our instruments, with a spectroscope, we are indeed able to know what the structure of this nebula is. It is the case of a model created using one of the initial versions of the ShapeX software application. The authors of this software are Dr. Wolfgang Stephan and Dr. Nico Konin. In this type of software, our approach involves proposing a structure, which in this particular case is a sphere. Subsequently, we randomly place some points within the sphere. And then those points, what we do is pass them through a slit. We make use of a slit, which is obviously virtual, just like the object itself. However, we implemented a speed law for those points, creating the illusion of a radial expansion. So naturally, when we eliminate the slit, which in this instance would be the occurrence in the middle box, we are left with the small ball containing dots. And as those dots expand, we pass through a slit, and the result we observe is an ellipse of velocities in the third box. The question is, why does this happen? Due to the fact that the expansion of the object takes place in a radial direction. Let's imagine that this is the expanding nebula. So, as you can see, the expansion is radial. And if I observe it accurately in the center, the speed of expansion will be entirely visible to me, providing a clear indication of its magnitude and direction. However, at any other point, if we are only able to know the radial velocity, we would see a component of the total velocity. And the other interesting thing is that up here, at the poles, you wouldn't see anything, as it expands radially, but lacks a component. That generates an ellipse for me. Why? Because just like this ball, where I can see the components in front and behind, that is the ones that approach and the ones that move away, the same thing happens with planetary nebulae, because their density is so low that we can see the emission from the part of the shell that is coming towards us and the part of the shell that is moving away. And that causes us to have a split, resulting in a double play, as the spectral lines are split and divided into multiple components. So the splitting is at its maximum when we are positioned in the center, that is, in the direction of the central star. And as we ascend or descend from the central portion, we will only experience a component of radial expansion, rather than the entire velocity observed in the central portion. So, the expansion is radial, expanding outwards from the center in all directions, radial with respect to the sphere, but I mean radial with respect to our line of sight. The component that goes in the line of sight is decreasing, until reaching zero in the polar part. Due to the expansion, the pole part experiences an upward direction of expansion and does not possess any components within my line of sight. That is the elliptical shape resulting from the spherical expansion shown in the third figure of our analysis. And And this is an authentic observational example case that serves as a genuine illustration of the concept. This is the Owl Nebula. This is a portion of what constituted the undergraduate thesis of Monica Blanco, who is currently a doctor. So, in Monica's thesis, we had observations made to the Owl Nebula, which is a spherical shell. And they can see, for example, that in slit C we almost pass through the center. In the other slits we are not passing through the center. And we are able to observe the spectrum of those slits in the figure that follows, where the velocity ellipses are visible, and indeed ellipse C is the largest ellipse in terms of longitudinal scale, isn't it true? It also looks brighter, and there we can effectively see that it is the maximum expansion, and the speed at which that gas expands can be estimated. So, that is one of the most amazing aspects of this kind of job, that we do not require the distance, for instance, or we require an additional parameter to determine the velocity in physical units of kilometers per second. Measurements in the International System of Units are of utmost importance and cannot be underestimated. So it is utilizing the Doppler effect method, which enables us to obtain information about our objects and enhances our understanding of them. And as an example of the complexity of nebulae, we have the NGC 6309 nebula, which was featured in an article we published in 2008 to demonstrate how intricate these objects can be. In which we encounter a multitude of cracks, it appears that we ultimately arrive at the L-shaped crack in that particular area. So there are a total of more than 10 slits that we have strategically positioned in that area. And among other findings, we discovered that the nebula, that had spiral arms resembling those of a galaxy, thanks to the implementation of spectroscopy, we discovered that it was indeed a nebula with a bipolar structure. So yes, it can be much more complex than a sphere. Planetary nebulae have very rare morphologies. And then, well, with this we can start getting to know each other. Spectroscopic data. The data we obtained in the initial job of 2008 proved instrumental in discovering this bipolar nebula. And later, we took much deeper and higher quality images, and it is perfectly clear that the nebula is bipolar. We took advantage of that work to also model, using the shape program, the structures that we had already found in the previous work. And this was a component of Gabriel Rubo's master's thesis. Therefore, the conclusion that I placed on this transparency is that if you have a desire to understand the morphocinematic structure of an extended object, Mezcal is the suitable choice for you to explore and gain insights from.